In this lecture video, we're going to talk about solubility equilibrium. Now, in our previous class, Chemistry 162, we spent a lot of time talking about equilibrium. We looked at equilibrium for different phase transitions, and we looked at equilibrium for chemical reactions, and we focused on it a lot when we looked at acid-base reactions. In this quarter, in this chapter, we're going to focus on the equilibrium that occurs when a solid dissolves in water. And we're going to look at compounds that we formally refer to as insoluble. So I have a precipitation reaction shown right here. It's the formation of bismuth sulfide. When we combine a compound or a solution that has bismuth ions and then a separate solution with sulfide ions, they'll combine to form a precipitate, a solid it forms. It's this beautiful red precipitate right here. And we've referred to these as just insoluble in the past. But when we looked at solution formation, we talked about how there's always some amount of our solid dissolving in the water and some amount of that dissolved solid recrystallizing onto the solid surface. When we see something as insoluble, it just means there's very little of that compound that's actually dissolved in the water. And instead of thinking it as soluble and insoluble, now we're going to actually apply our what we know about equilibrium to that solution formation process. So previously, we looked at these solubility rules for deciding if a precipitate would form in a chemical reaction. And we would say it's either very soluble in water or it's not soluble in water. And we alluded to the fact that this is more of a spectrum than black and white, soluble or insoluble. And now we're going to really dive into that. So all of these compounds on our solubility rules that would form an insoluble compound will still precipitate at a reaction. And we're going to start calculating how much of that solid is actually dissolving in the water. So just to refresh on equilibrium, dynamic equilibrium is when you have either a chemical reaction where the rate of the forward and reverse reaction are the same, or if you're looking at a physical transformation like evaporation, you're at dynamic equilibrium when the rate of evaporation is equal to the rate of condensation. Looking at the formation of a solution, when we're at dynamic equilibrium for solvation, we will have the rate of solution, which is this one right here, the solid particles becoming surrounded by water molecules and dissolving into the liquid. That rate of solution will be equal to the rate of recrystallization, where those ions dissolved in the solution come back to the solid and form as part of the solid again. So we have the rate of dissolving or the rate of solution will be equal to the rate of crystallization when we're at equilibrium. And that means that when we're viewing this solid in the liquid, it won't be changing. It won't be decreasing in volume. It won't be slowly dissolving or forming a precipitate. It'll just look like it's sitting at the bottom of a flask. So we can calculate an equilibrium constant for this, just like we did for chemical reactions. The equilibrium constant, which is always a uppercase K, is going to be equal to our products over our reactants. And in this case, we're thinking about the process of this solid dissolving. And so our reactant will be a solid, and our products will be aqueous ions. So let's take a look at this. So looking at the equilibrium constant for a chemical reaction, we can generalize it like this, which is kind of a lot to look at when we replace actual elements with variables instead. So I like looking at the example first, and that allows me to interpret the variable formation. So we're going to look at lead chloride. So lead chloride will be a solid in water. It's insoluble. But some small amount of it will be in equilibrium, where we have some of our lead plus 2 ions and 2 chloride ions in solution, and so dissolved in the water. So if we're going to write our equilibrium expression for this, and we're going to have our products over our reactants, our products are going to be the aqueous ions, and our reactants will be that solid lead chloride. So if we were going to write this out, we would have our products on top, our lead +2 ions and our chloride ions, and it would be then divided by our lead chloride. But because this is a solid, that means we have a situation with a heterogeneous solution, or equilibria, and we are going to not include solids when we calculate our equilibrium constant. We can't measure its concentration in water like we can the lead ions and the chloride ions. And so we don't include that solid. And our KSP, or our equilibrium constant, is going to just be equal to that lead ion concentration times the chloride ion concentration squared. Remember, we're taking that coefficient 2 in front of the chloride and squaring the concentration of our chloride ions to account for the increased concentration of these ions that we'll have based on this mole ratio of our chemical reaction. And so that gives us our equilibrium constant. And we're going to call that our solubility product rather than equilibrium constant for solvation. And I don't have a great reason why. So our solubility product will be just equal to our products when we're looking at these chemical or these physical transformations. We're going to track something else. It's called molar solubility. Come down here. Solubility is going to be the amount of our solute that actually dissolves in the water, if we're looking at something that's aqueous. We've already learned about solution formation when we were looking at intermolecular forces, that temperature will play a big role in how much of our solid will actually dissolve. So if we have sugar and we add it to water, some of it will dissolve, not a ton. But if we heat it up, we'll be able to get a lot more to dissolve. And that's the recipe for simple syrup. There you go. So it's temperature dependent. So keep that in mind. We'll always be reporting molar solubility for a specific temperature. And molar solubility is essentially going to be the concentration. It's the number of moles of solute that are going to dissolve in a liter of a solution. And so here what we're doing is we're using molarity rather than molality, which would be in kilograms of solution. We're going to focus on volume. And so what we're looking for, what our molar solubility really is what is this concentration of ions that we have in solution? And we'll be correcting for the coefficient right here. And so it will be kind of our base amount. Another way to think about it is what is the amount of our product, reactants, the amount of our solid that is dissolving in water. That is our solubility product, or our molar solubility. So we use a large S for this. Different textbooks actually use different variables for molar solubility. I tend to think of it as X personally. And we've got this lovely equation right here for calculating what that solubility will be, what that concentration of ions is in solution. And we'll walk through an example of this. So you'll see it's kind of Genesis. We can plug into this equation, but like all other equilibrium problems we did before, we can also solve this using an ice table as well. So, get into it. We're going to do a couple of examples here. They're listed in your lecture slides. We're going to look at the molar solubility of lead chloride in pure water, and then we're going to calculate the solubility product of lead to bromide in water. If we know the molar solubility. So we'll go for both directions in a following video. If you'd like to try out this problem first beforehand, before viewing the solutions, I recommend doing that.